Hello and welcome to my next GCSE science video on visible light and EM electromagnetic waves. Now, Ptolemy, the great Greek astronomer, said that the Earth was the centre of the universe, which we know is wrong. The Polish astronomer Nicholas Copernicus thought Ptolemy's measurements fitted a different model because Ptolemy used measurements of the movement of the objects in the sky to explain how the sun, moon and the planets moved in orbits. But Copernicus said that this model fitted more with the sun at the centre of the solar system. The church did not like this heliocentric. Geocentric is the earth at the centre, heliocentric is the sun at the centre. And the priest inserted an introduction into Copernicus' book before it was published, saying that the book contained ideas with no proof. But the great astronomer Galileo Galilei discovered 4 of Jupiter's moons, and by plotting their movements he showed that not everything orbited the Earth. This and other observations led to him to support Copernicus' idea, and the church was still against the idea, and Galileo ended up being put under house arrest 10 years later. Now, there are 2 types of telescope: refracting telescope and reflecting telescope. Now if you look to the right of the page, this is what refraction is. Refraction is when light or anything enters a different medium, so from air to liquid or liquid to solid even, it will slow down or speed up. In this case, if you look, light is moving through the air, enters the water, and it will bend because it is changing speed. You have an incidence angle and a refraction angle. The line down the middle is called the normal. Now the incident angle is bigger than the refractive angle. And this is what refraction is. It means that you can cause light to kind of change course. So instead of light going straight, you look at now on the left, light enters the lens straight, bends, and then comes out straight because it's being refracted. And this is a refracting telescope works. It has a convex lens, which means light will bend and go inwards until it meets a certain point and then goes outwards again. Now a convex lens, just to say, is a glass block that is curved on both sides to make it thicker in the middle. And then light rays entering a lens from the air are brought together or converge, because it also can be called a converging lens. And then you have an eyepiece lens, which is where the object is seen. Reflecting telescope. Now, this usually happens when light hits an object. Some of it will refract, but some can be reflected. It will bounce back off. Now, if you look here, what will happen is the 2 straight lines is light coming down onto the primary mirror. The mirror then reflects it. Now, as you can see, it's curved, so it reflects it inwards till it meets a point, and that's the secondary mirror, which is bounce it off to the eyepiece. Light, you have light and sound waves. Now all waves transfer energy, and this is the simple model of what a wave is. Now a few definitions: the distance between one crest and the next crest. Now the crest is the highest point on the wave. That's a wavelength. It can also be between a trough, which is the lowest point on the wavelength. So the distance between 2 crests next to each other, or 2 troughs, is the wavelength. Now as you can see, there's a straight kind of line going in the middle of the wave, but that's exactly halfway between a crest and a trough. We'll just call that the normal for now. The distance between the normal and the crest or trough is the amplitude. That's the highest amount of displacement, we call it. Displacement is the distance from the normal line, just how far it's gone up. Now maximum displacement is amplitude. It's a little bit of AS, you don't essentially need to know that, not at this stage anyway, but it's just good to know. And then an oscillation is the distance between one point on one wave and the same point on the next wave. But now that has to be at the normal, so it can't be anywhere on the wave, it has to be at the normal part. Now let's say amplitude is measured in meters, wavelength is measured in meters, And you also have something called frequency. Frequency is the number of waves passing a point each second. Now, a period is the amount of time it takes for one wavelength to occur. Frequency is the number of waves passing a point each second. We'll look at that next. Anyway, two types of wave. You have longitudinal, which are sound waves, and transverse, which are light waves. The important thing, transverse waves oscillate at 90-degree angles to the direction of movement. So you see light transverse, that's going along the page, but it oscillates up and down. Sound and longitudinal waves, they oscillate in the direction of movement. So it's going along the page and it is oscillating sideways. Some calculations you need to know. As I said, frequency is 1 over the period. So if they said it takes a wave 0.5 seconds to have one oscillation, then you would know that the frequency is 1 divided by 0.5, which is 2, so the frequency was 2 Hertz. Now speed, v is velocity, equals frequency, f, times lambda, which is the kind of upside down y, which is wavelength. Now, so for example, if you're given a frequency of 2 Hertz and a wavelength of 1 meter, the speed would be 2 meters per second, because our period is measured in seconds. Frequency is 1 over second, so we say second minus 1. Wavelength is measured in meters, so velocity is measured in meters times seconds minus 1. Second minus 1 is just 1 over second, so meter over second. Now, I don't think you need to be too worried about how to get those units or where they come from, but I'm just telling you just in case. If you find that confusing or want a little bit better explained, email me, ask in the comments. Now you have the visible light spectrum. That's any colour you can see today is part of the visible light spectrum, and that's between 400 nanometers in wavelength, so very small wavelength, to 700 nanometers in wavelength. Blue light is shorter, 400 nanometers. Red light is longer, 700 nanometers. And either side of the visible light, you have different types of transverse light waves. Now, this is the whole electromagnetic spectrum. You have the shortest wavelength and highest frequency. They are in their opposites. The larger the wavelength, the shorter the frequency. The shorter the wavelength, the larger the frequency. So the shortest wavelength is gamma rays, then X-rays, ultraviolet, visible light, infrared, microwaves, radio waves. And then, so radio waves can be kilometers long in wavelength. Gamma waves will be incredibly short, like times 10 to the minus 12. That's really small, but will have a very high frequency, so there'll be many of them per second. But wavelength radio waves will be very few per second, if any. Now, there's a common thing with all electromagnetic waves is that in a vacuum, that's where there's no particles at all, it travels at 3 times 10 to the 8 meters per second, which is very fast. That is roughly, well, it is 3 times 10 to the 8 is a very rough thing. It is 3 with 8 zeros, so a lot. Now, William Herschel was a British astronomer. He put dark coloured filters on his telescope to help him observe the sun safely. He noticed that different coloured filters heated up his telescope to different extents. He wondered whether the different colours of light contained different amounts of heat. To test his idea, he used a prism to split sunlight into a spectrum and then put a thermometer in one of the colours. He placed 2 other thermometers alongside of the spectrum. As he changed the colour from violet to red, he found that temperature rose. Herschel wondered that what would happen if he measured the temperature just beyond the red end of the spectrum, where there was no visible light. He found that this gave the highest temperature. He discovered infrared waves. That's more than red. Just remember, you have violet at the short end of the visible light, red at the longer end of the visible light spectrum. Infrared is beyond red, ultraviolet is beyond violet. Johann Ritter found out about Herschel's work in in 1801 set about trying to find invisible rays at the other end of the spectrum. He used silver chloride, a chemical that breaks down to give a black colour when exposed to light. It was already known that silver chloride turned black more quickly in violet light than in red light. Ritter showed that silver chloride turned black fastest when exposed to invisible rays just beyond violet. These were called ultraviolet. Now you have dangers of waves. Infrared, they can cause burns, because of course they are particularly associated with heat. Ultraviolet can cause skin cancer, especially the more high frequency, lower wavelengths, that's nearer the X-rays sort of UV. X-rays and gamma rays can cause mutations and cancer. Uses. Right, visible light is vision. Ultraviolet can be used in fluorescent lamps and can also be used because some insects and arthropods have ultraviolet light. You can use an ultraviolet light to show these insects, like scorpions. They're one. If you shine an ultraviolet light over them, they will fluoresce back. X-rays are used in scanners to detect fractures and broken bones. Infrared can be used in CCTV and heat vision. So you ever see like the red and blue heat vision thing? That's infrared. Radio waves are used in communication, TV, all sorts of things like that. I've missed off microwaves. Microwaves are often used to heat food. And gamma rays can be used for sterilisation and radiotherapy. Weirdly, they can also kill cells as well as causing cancer. So they can be good and bad. Ionising radiation. Now, why gamma rays cause an increased risk of cancer is because they are ionising radiations. Such radiation can remove electrons from atoms to form ions. Ions are charged particles. That's all you need to know. There are 3 types of radiation: alpha particles, beta particles, and gamma waves. Alpha particles are just a helium nuclei, 2 protons, 2 neutrons. Beta particles are just electrons. And then gamma rays, the one at the bottom, they are part of the electromagnetic spectrum. And alpha and beta particles, they are not electromagnetic radiation, they are particles. And what happens is they will collide with atoms and knock off electrons to form ions. Radio waves can give them energy which causes them to be emitted. So thank you for watching. Any questions, please ask, like, comment, whatever, email me. And thank you for watching, and goodbye.